Here, for x is equal or larger than 0, find the local max and min, and inflection points for the function g of x equal to x multiply e to the negative x and sketch g of x. So the first step we want to do is find local max or min. So to do that, what we need to do, we have to find a critical point, and then we need to test this critical point to see if they are local max or local min or either. So to find a critical point, it's where the first derivative is 0 or undefined. So we have given this function g of x equal to x e to the negative x. So to take the derivative, what we're gonna use the product rule. Since this is two multiplied function, I'm gonna assign x to u and then v to e to the negative x. Now I'm gonna take the derivative of u and v. Derivative of v is just using the chain rule. Now I'm ready to apply the product rule. It's gonna be u prime multiplied by v plus u multiplied by v prime. So 1 multiplied by e to the negative x and then plus negative, I blot the negative x e to the negative x. Now we can factor e to the negative x, and that's our derivative. Now let's find the critical point. It's where the first derivative is equal to 0 or undefined. So first, for undefined, this function here, the first derivative, is all defined for all values of x. So we will just use where the first derivative is equal to 0. Now note, e to the negative x is never 0. If we block x for 0, or if we block x is negative value or positive value, it's never 0. So I'm gonna take only the term 1 minus x and equal that to 0. So that's gonna result in x equal to 1, and that is our critical point. So again, our first derivative function is e to the negative x multiplied by 1 minus x. Now, second step is to test this critical point to see if it's local maximum or minimum or either. What I'm gonna do here, I'm gonna use the second derivative test. We can use the first derivative test if we want, but here I'm gonna apply the second derivative test. So what I'm gonna do, I'm gonna take our critical point and evaluate it at the second derivative, and I want to see what are the signs. So first we have to find the second derivative, which is just the derivative of the first derivative. So what we're gonna do, I'm gonna use the product rule in here. I'm gonna assign k to the e minus x and h to 1 minus x. Now I'm gonna take the derivative of each. Here note that our function is g of x, not f of x. So here I'm ready now to apply the product rule. So for the first term, I'm gonna multiply k prime by h, and then for the second term, I'm gonna multiply k by h prime. Now they're gonna be minus e to the minus x, and then 1 minus x, and then minus e to the minus x. Now what I'm gonna do, I'm gonna vector e to the minus x. So, and also note the negative sign, so it's gonna be minus 1 plus x and then minus 1, and that, if we simplify it, gonna be e to the minus x and then minus 2 plus x, or x minus 2. So now this term is the second derivative of the g function. Now what we want to do, we want to evaluate our critical point in the second derivative. We want to know what are the signs. So our critical point is 1. So I'm gonna plug x for 1. Note that e to the minus 1 is never 0, it's positive. And then the second term is negative, so multiply negative by positive, it's gonna result in negative sign. So the second derivative evaluated at the critical point is negative, which means the shape of our graph is concave down. It will look like something like this. And therefore, what we notice, the critical point is a local max since we have concaving down. Now, to find our inflection point, two conditions has to be met. The first condition is a possible inflection point is where the second derivative is 0 or undefined. To confirm that the possible inflection point is actually an inflection point, we have to do a test. So our second derivative again gonna be e to the negative x, then multiplied by x minus 2. Now this term is defined for all x values. So now what we have to care about is second derivative is equal to 0. So second derivative is going to be equal to 0, where e to the minus x, x minus 2 equal to 0. Notice this term, e to the minus x, is never 0. So it's only going to be x minus 2 equal to 0. Then that will result in x equal to 2. X equal to 2, this is a possible inflection point. So we have to test if it's actually an inflection point. So what I'm gonna do here, I'm gonna draw an x number line. I'm gonna mark our possible inflection points. And then I want to see what are the behavior or the sign of the second derivative if we take a value that is larger than our possible inflection point and is lower than our inflection points. So here what you notice, I picked 0 and 3. That is larger and smaller than our possible inflection point. You can take million or minus million if you want to. This is just a randomly selected. So I'm going to evaluate this value in the second derivative. So I'm going to evaluate now 0 on the second derivative. So we notice the first term is always positive, so the second term is negative. Negative by positive gonna result in negative sign. And then I'm gonna take x equal to 3, and I want to know what are the signs at the second derivative. Notice this is not minus 3 minus 2, it's actually plus 3 minus 2. So I'm gonna fix this. So plus 3, then it's gonna result in a positive sign in here. So positive multiplied by positive will result in a positive sign. Now I'm gonna mark these signs in our number line. So we are going from negative to positive. So the test says if there is of the second derivative signs changes around our inflection point, possible inflection point, it is actually an inflection point. Now what we want to do, we want to graph the function, and we found that critical point with a local max at x equal to 2, x equal to 1, and then our inflection point is at x equal to 2, and we want to draw it where x is greater than or equal to 0. So notice here, this is our local max and this is our inflection point.